Assalamualaikum and hello everyone. So today we are going to discuss on chapter 12 question. Chapter 12 is heat conduction and thermal expansion. Okay, without wasting time, let's discuss. Calculate the heat transfer. Alright, so the question asks us to calculate the heat transfer. The heat transfer is Q. In 24 hours, through a 2.4 meter square metal sheet. So 2.4 meter square is the area of the metal sheet, which have the thickness of 1 centimeter. As when the temperature difference between the surface is 0.5 degrees Celsius. The temperature difference is 0.5 degrees Celsius. Given the thermal conductivity coefficient of the metal is 16 watt per meter per Kelvin. And we know the formula for rate of heat flow is dQ over dt, which is Q is the heat transferred and T is the time taken, equals to negative thermal conductivity and times area and also the temperature gradient. The temperature gradient is dt over dS, where dt is the changes in temperature. So now the question asks us to look for the heat transfer. Alright, so we know the heat transfer is Q. We are going to look for Q, dQ. And what we are going to do now, we are going to times time with this equation. So we will get negative thermal conductivity times the area times the temperature gradient and also times the time taken. So the thermal conductivity is 16 watt per meter per Kelvin. The area given is 2.4. dt is the changes in temperature, which is 0.5 degrees Celsius. So it has negative due to change in temperature. And also the thickness is 1 centimeter. We have to change it into meter times by the time taken. So the time is 24 hours. We need to change it into second. So 24 times 60 times 6, 60. We have 24 hours and we know 1 hour we have 60 minutes and 1 minute we have 60 seconds. Now you press the calculator, you will get your heat transfer 1.66 times 10 to the power of 8 joule. Okay? So that's all for question 1. Let's proceed to question 2. A composite rod is made by joining a copper rod. Okay, joining. The keyword is joining. Joining what? Joining copper rod which diameter 4 cm with an iron rod of similar diameter. Okay, one trick that I want to teach you when you see the word diameter and it says similar, you must know the area is the same. So area of copper is equals to area of iron because similar diameter. The rod is insulated and its ends are kept at 2 different temperatures. As you can see, the temperature for copper is, at the end of the copper, is 160 degrees Celsius, whereas the temperature at the end for iron is 40 degrees Celsius. The coefficient of thermal conductivity of copper is 385 watt per meter per Kelvin. So this is the thermal conductivity for copper, whereas 80 watt per meter per Kelvin is the thermal conductivity for iron, respectively. At a steady state, determine the temperature at the joint. So the temperature at the joint. So where is the joint? The joint is here. So I refer the temperature at joint as, I will write it as temperature copper iron. So here will become temperature copper iron. So because they are joined, they will have the same rate of heat flow. Alright, they will have the same rate of heat flow. So dQ dt of copper is the same as dq over dt for iron. And we know the formula for heat flow is negative K, but this is for copper. I'll make it as thermal conductivity for copper times the area of copper times the temperature gradient. So temperature of copper over dx of copper equals to negative K iron equals to area of iron, and then the temperature for gradient for iron. Okay, now we know dTv and dTi is the temperature difference. So we're going to rewrite this equation. We will get temperature difference. Alright, so the temperature difference for copper will be temperature copper iron minus temperature of copper divided by length of copper. Okay, why temperature of copper iron minus temperature copper? You must know one thing. Temperature difference will always be final temperature minus initial temperature. So for the copper case, at the end of the rod of the copper, this is the initial temperature, and here is the final temperature. This is the initial temperature for copper, and this is final temperature for copper. Whereas for iron, the temperature at the joint will become the initial temperature of iron, and here will become final temperature of iron at the end of the rod. So we must know temperature difference will always be final temperature minus initial temperature. Okay, let's continue with thermal conductivity of iron times area of iron, and for iron it's going to be final temperature minus initial temperature. So for iron, the initial temperature is at the end of the rod, so initial temperature of iron minus final temperature of iron, which is Ti, minus the temperature at the joint, which is copper iron, divided by length of the iron. So as we know, area of copper is the same with the area of iron, so we can ignore the area. Now let's substitute all the information given. So thermal conductivity for copper is 385, and then the temperature copper iron, which is the temperature joint, we are looking for it, and the temperature of the copper is 160 degree. Okay, and then the length of the copper is 8 centimeter. We change it into meter. So equals to thermal conductivity of iron, which is 385, and then the temperature of iron at the end of the rod is 40, minus temperature at the joint, temperature of copper iron, and also the length of the iron, which is 5 centimeter, where we change it into meter. So you rearrange this equation and you press your calculator, you will get the temperature of copper iron, or temperature of joint at the joint, is 130.01 degrees Celsius. Yes, that's all. Alright, let's proceed to the next number, question 3. A 0.2 meter times 0.2 meter glass window has a thickness of 5 mm. So we know 0.2 meter times 0.2 meter is the area, whereas the thickness of 5 mm is the S. Calculate the rate of heat transfer. So when there is the word of rate, we know it is per time. So the rate of heat transfer is dq over dt through the window if the temperature difference is 35 degrees Celsius. The coefficient of thermal conductivity of the glass is 0.63 watt per meter per Kelvin. So we know the formula for rate of heat transfer is dq over dt equals to negative K times the temperature gradient. So we are looking for the rate of heat transfer, and we know the thermal conductivity of glass is 0.63, and the area is 0.2 times 0.2, and the temperature difference is 35 degrees Celsius, and the thickness is 5 mm. We change it into meter. So 5 times 10 to the power of negative 3 because I changed it to meter. And you press your calculator, you will get rate of heat transfer 176.4 watt. Okay, for your information, why is the unit in watt? It is because heat flow, heat transfer is energy. So we know if energy over time, we will get power. And the unit for power is watt. Okay? Alright, that's all for question 3. Let's proceed to question 4. The area of a metal plate changed from 120 meters squared to 120.059 meters squared. So D is the initial area, whereas D is the final area. When the temperature increases by 30 degrees Celsius, so this is the temperature difference, calculate the coefficient of linear expansion of the metal. So, linear expansion, coefficient of linear expansion. We know changes in area is coefficient of area expansion times the initial area times the temperature difference. So, this is coefficient of area expansion. And we also know coefficient of area expansion is also equals to 2 times coefficient of linear expansion. And this is coefficient of linear expansion. So now we are looking for coefficient of linear expansion. So this is going to be your equation number 1 and this is going to be your equation number 2. So what we're going to do, we are going to substitute equation 2 into 1. So when we substitute, we will get changes in area and the coefficient of area expansion we're going to substitute with 2 times coefficient of linear expansion times the initial area times the temperature difference. And we know changes in area is also equals to final area minus initial area. So here will become final area minus initial area equals to 2 times coefficient of linear expansion times initial area times the changes in temperature. So I'm going to rearrange this equation until I get the coefficient of linear expansion as the subject. So when I rearrange, I will get changes in area divided by 2 times initial area times changes in temperature. So put all the information you have. We know the final area is 120.059 minus 120, the initial area, 2 times the initial area, which is 120, and the temperature difference is 30. So press the calculator, you will get coefficient of linear expansion is 8.19 times 10 to the power of negative 6 per degree Celsius. Per degree Celsius. So the unit for linear expansion of the metal is per degree Celsius. So that's all for question 4. Alright, now let's proceed to question 5. The dimension of an aluminium wire at a room temperature 27 degrees Celsius is 115 meter long. So the length of the aluminium wire is 150 meter. And the cross-sectional area for the aluminium wire is 3 times 10 to the power of negative 6 meters squared. It is then melted to form a spherical ball. So from aluminium wire, then it will melt to form spherical ball. If the coefficient of linear thermal expansion of the aluminium is 22.2 times 10 to the power of negative 6 per Kelvin. Okay, so this is the linear thermal expansion, coefficient of linear thermal expansion. Calculate the volume of the spherical ball at room temperature. So at 27 degrees Celsius. So one thing that you need to know, the volume for aluminium wire is same as the volume of the spherical ball. Okay, I put the spherical ball as sphere. Why? Because aluminium wire is melted to spherical ball, so they will have the same volume. And we know the formula for volume can be area times length. So the area given is 3 times 10 to the power of negative 6 meter squared, and the length given is 150 meter. So when you press the calculator, you will get 4.5 times 10 to the power of negative 4 meter cube. So this is your initial volume. Alright, next one. Change in the volume of the sphere if it is heated to 200 degrees Celsius. Change in the volume. So we are going to look for change in the volume at 200 degrees Celsius. If it is heated at 200 degrees Celsius. So how are we going to tackle this question? So first of all, we know changes in volume is equals to coefficient of volume expansion times initial volume times changes in temperature. Okay, we have the information for the initial volume and we can find for the changes in temperature, but we don't know the value for coefficient of volume expansion, but we can find for it. How? Because we know coefficient of volume expansion is equals to 3 times coefficient of linear expansion. So what we're going to do, this is going to be your first equation and this is going to be your second equation. You're going to substitute equation 2 into 1. So when we substitute, we will get 3 times coefficient of linear expansion times the initial volume times the changes in temperature. So we know coefficient of linear thermal expansion is 22.2 times 10 to the power of negative 6, and the initial volume we already calculated in question A, which is 4.5 times 10 to the power of negative 4, and the difference in temperature, changes in temperature, will be 200 degrees Celsius minus 27 degrees Celsius, which equals to 5.18 times 10 to the power of negative 6 meter cube. So this is the changes in temperature. So changes in temperature is final temperature minus initial temperature. So the initial temperature is 27 degrees Celsius because it's say at the room temperature. Now we are going to look for the next question. Change in the volume of the sphere if it's cool to negative 7 degrees Celsius. Just now it's heated to 200 degrees Celsius, but now it's cool to negative 7 degrees Celsius. So we are going to use the same formula, which is changes in volume equals to 3 times coefficient of linear expansion times the initial volume and changes in temperature. So we know coefficient of linear expansion is 22.2 times 10 to the power of negative 6. Initial volume we calculated in question A, 4.5 times 10 to the power of negative 4, and also changes in temperature. Now the changes in temperature will become, the final temperature is negative 7 and the initial temperature is 27. And when you press the calculator, you will get the changes in volume negative 1.01 times 10 to the power of negative 6 meter cube. Alright, so we are done with question 5. Okay, let's proceed to question 6. The length of metal bar is 300 cm at negative 30 degrees Celsius. Given the coefficient of linear expansion of metal bar is 11 times 10 to the power of negative 6 per degree Celsius. Calculate the length of the bar at 80 degrees Celsius. Alright, we know changes in length equals to initial length times coefficient of linear expansion times changes in temperature. Okay, so what we are going to do, we know changes in length, we will get, okay, let's look for changes in length. So the initial length given is 300 centimeter. Change it into meter and then times with the coefficient of linear expansion, which is 11 times 10 to the power of negative 6, and also times with the changes in temperature. So the final temperature is 80 degrees Celsius and the initial temperature is 30 degrees Celsius, negative 30 degrees Celsius. So this is the changes in temperature, which is final temperature minus initial temperature. So you will get your changes in length is 3.63 times 10 to the power of negative 3 meter. But the question asks us to look for length of the bar at 80 degrees Celsius. And we know changes in length is final length minus with initial length. So we know the changes in length is 3.63 times 10 to the power of negative 3. And in the final length, we are going to look for it. And the initial length is 3 meter. So when you press the calculator, you will get and rearrange the equation. You will get the length 3.00363 meter. So this one I change it into meter, or you can do it like this, 300 times 10 to the power of negative 2. Okay, because I changed it into meter. So this is the final answer. Okay, final question. A 200 centimeter cube glass cylinder, okay, so the volume of the glass cylinder is 200 centimeter cube is filled to the brim with a mercury at 27 degrees Celsius. So this is the initial temperature. Calculate the amount of overflow when the temperature of the system increases to 200 degrees Celsius. So this is the final temperature. The coefficient of linear expansion of the glass and mercury are 4 times 10 to the power of negative 6 per Kelvin and 6 times 10 to the power of negative 5 per Kelvin. So they will become the coefficient of linear expansion of the glass, and this is the coefficient of linear expansion of mercury. So calculate the amount of overflow. We are going to calculate the changes in volume. So changes in volume overflow equals to coefficient of volume expansion times times initial volume and times changes in temperature. So as we don't have the information for coefficient of volume expansion, we know coefficient of volume expansion is 3 times coefficient of linear expansion. So what we're going to do, I'm going to substitute equation 2 into 1. So sub 2 into 1. So changes of volume overflow is equals to 3 times coefficient of linear expansion times the initial volume times the changes in temperature. And we know coefficient of linear expansion is going to be coefficient of linear expansion of mercury minus coefficient of linear expansion of glass times the initial volume times the temperature difference. So now we are going to substitute all the information we have. Linear expansion of the mercury is 6 times 10 to the power of negative 5, whereas coefficient of linear expansion of glass is 4 times 10 to the power of negative 6. Times the initial initial volume. So the initial volume is 200 centimeter cube. And the temperature difference. Temperature difference is going to be the final temperature minus the initial temperature. So the volume of the overflow when you press the calculator is 2.5 centimeter cube. So why if the unit is in centimeter cube? Because I didn't change the unit for the initial volume. So I leave it also as centimeter cube. Okay, that's all from me. Thank you so much. Have a great day, everyone. Bye bye.